And it is my pleasure to welcome back for our second session Professor Hans-Peter Plag. He is director of the Mitigation and Adaptation Research Institute at Old Dominion University and professor of Ocean, Earth, and Atmospheric Sciences. And Dr. Plag, welcome back. We're so glad to have you here. And I turn it over to you.
Well, thank you very much. And first of all, a happy Mother's Day to all the mothers that are on today. I think that's an important day for humanity to celebrate. And I have to share my screen, so I'll do that as the first thing. And let me see, where is, I think you can already see my screen.
I can, yes, I can see it, Dr. Plag.
Okay, so, well, thank you very much for inviting me again. Last week we talked about the modern climate change, and we talked about the baseline. I tried to show you that we have a planet that had been relatively stable for a long time. The first point I made last week was that it's very important to take a view on the planet from a distance and not look at it from the perspective of a human being who has a lot of interest and a lot of biases. And if we look at the planet too much from our personal view, we don't really see what is going on. And coming in a spaceship and looking at the planet, we would notice that the Earth's energy imbalance is very, very large, very much out of the normal range that we would see for a planet. And then I posed two questions. One was, why did the Earth's energy imbalance increase so dramatically? And where and in what form is the energy stored, and what are the consequences? There are two more questions that we will add today, but I think these were the basic questions I started to talk about. And when we talked about the baseline, the main point that I wanted you to take home on last Sunday was that during the Holocene, which is the last ecological epoch, the climate and sea level were exceptionally stable. So we don't really see in the Earth's history, at least for the last few 100,000 years, we don't see any period where the planet was as stable as it was in the last 12,000 years. And that made the Holocene a very safe operating space for humanity, and it allowed us to emerge as a dominant species on this planet. And today we would like to look at the symptom of modern climate change, and hopefully we will be able to get through the diagnosis as well. And one point I want to make, because many people do not probably realize how we actually know all of the things we are knowing about the planet. And I don't have time, of course, to go into details, but I want to show you just a few examples. We have an enormous amount, and we actually spend also a very large amount of money on that. We have an enormous amount of observing systems all over the planet, on land, in the ocean, in space, that gives us a huge amount of data. So what we can really say, and if I would speak about that, we would need more than 3 lectures to really understand how well we know what is going on with the planet. So humanity has an enormous amount of data, and we have all the knowledge. We have not, if something goes wrong, we no longer have the excuse that we didn't know, that we were not able to predict, not able to foresee. If we don't prepare, if we don't do something about what is happening, we have no excuse that would really tell us, yeah, we just didn't know. So the knowledge does not turn into power. And some years ago, I wrote a column about this with this little picture down there where all the adults are staring at the fire and they don't see the water that would be so easy to get and do something about the fire. We will talk next week about what we could do to change the situation. But today I would like to describe the fire a little bit more so that we really understand what is going on with the planet. And we have, as I said, a huge amount of data. I showed you this picture already last week. It basically shows the temperature anomaly or the temperature compared of 2008 to 2012 compared to 1900. And we see that in many places, the temperature has changed by 2 degrees Celsius or even more, 4 degrees Fahrenheit, the mean temperature averaged over the whole year. And we can see that this is not evenly distributed. The Arctic has increased much, much more in temperature, and in some parts over the ocean and in some parts in Antarctica, the temperature actually went down a little bit. And we have a huge amount of other things that we can see are changing. It's the snow cover that's getting less, the sea ice is getting less, upper ocean heat is increasing, sea level is increasing, and of course the greenhouse gases in the atmosphere are going up. I'm showing here on the right side the carbon dioxide as an example. And then the surface ocean gets more carbon dioxide and the ocean gets more and more acidic. But when we look at those diagrams, we do not fully understand what the extent of those changes actually means. To show you two examples, the sea ice and the temperature increase. If we compare it to a much longer baseline, then we can actually see how large the changes are that we had in the last 100 years or in the last 50 years compared to the long-term stable average. You see that the temperature in the last 100 years, the air temperature, went up rapidly, went basically through the whole range that we have experienced in the last 12,000 years. And sea ice, which was stable over a very long time, was decreasing rapidly in the Arctic. So we have a situation where stability has ended and we are in a very rapid transition. I showed you last week the lab sheet for am I still on? Hello?
You're here.
Okay, I just got a signal that I was reconnecting, so I don't know whether you lost a lot. So we got this lab sheet of planet Earth, and based on the data for the last 800,000 years.
Doctor, you need to reshare your desktop, please.
Okay.
There we go. We've got it.
Okay.
Thank you.
So what I was saying is last week I showed you the lab result for planet Earth based on the last 800,000 years. And what you can see is that the ranges that were happening during the Holocene, these are the dark blue boxes, are very, very small. And when we want to see where we are currently, then we can look at what happened, for example, what are the values by 2010? And you can see that carbon dioxide on the left side is by far out of the range that we had during the last 800,000 years. And as I pointed out, the 170 parts per million on the bottom of carbon dioxide corresponds to ice ages, and the 300 parts per million to warm periods. Now we are at 400 parts per million. If I would get a result like that, if I go to the doctor and give a blood sample, and I would get a result like that for cholesterol or blood pressure or temperature, I would be afraid. I would be totally outside of the normal range. The same is true for methane, the second one from the left. It's also true for the greenhouse gas forcing, the albedo forcing. The temperature is just at the top of the range because we were very low in 1900, and then it went up all the way to the top. And in terms of sea level, we have a very, very small change, and we are almost still in the normal range. So this is a lab sheet that is reason to worry. And when we look next week on the prognosis, then we will see that we are heading to even further away from the normal range. So with the greenhouse gases, they all are increasing. The carbon dioxide is increasing, the methane level is increasing. But again, those diagrams are not showing the real picture. What I did recently is I looked at what was really the values, for example, 20,000 years ago during a glacial maximum, we had 180 parts per million. At the beginning, when we transitioned to agriculture, it was 270 parts. And at the start of the industrialization in the 17th century, it was 280 parts per million. So what I did is I actually looked at my life in terms of carbon dioxide. I was born at 312 parts per million, already outside of the normal range. I started as a carpenter. When I was young, I was a carpenter, 320 parts per million at the university, 331. I got my PhD when it was 350. I got married when it was 373. And today it's 416. So what this means is that my age in carbon dioxide increase is 100 parts per million, 104, which is 1.5 parts per million per year. And the increase over the last 20,000 years was only 120 parts per million. So the increase during my lifetime was 250 times faster than on average during the pre-industrial 20,000 years. So we have really totally changed the way how greenhouse gases go into the atmosphere and cycle through the Earth system. This diagram is another way of showing this. 800,000 years, the carbon dioxide was in a very small range. But this range corresponds to 130 meters of sea level. It corresponds to 5 degrees Celsius or 10 degrees Fahrenheit in global temperature change. And we are expecting that it might go very, very much higher if we continue to do what we have been doing in the last 50 to 100 years. So 2 questions. What did this increase of carbon dioxide mean for the Earth's energy imbalance? And why are we not experiencing the full impact of the dramatic increase? It seems like we are not really feeling the 5 degrees Celsius that normally would correspond to what we are seeing here. So the Earth's energy imbalance, I explained this last week, is normally very, very small. 10 to the minus 10, 10 to the minus 9 of what comes from the sun stays on the planet. The rest goes back into space. And over the last 200 million years, the total energy that was stored on the planet was something on the order of 100 to 1,000 zetajoules. You don't have to worry about those units. I just use the numbers that are important. So over 200 million years, the planet stored something like 100 to 1,000 zetajoules. But then humanity became very active. And now the energy imbalance is 10 to the minus 3 during the last 70 years. And now the planet is storing 1,000 zetajoules in 1 century. So instead of doing this in 200 million years, the planet is now doing this in 100 years. And that gives you an idea how fundamental the change is that humanity caused to happen in the planet. So the Earth's energy imbalance increased by a factor of 10 million, on the order of 10 million. And the question is, where is this energy actually being stored? Why don't we feel a much higher air temperature? Why is it still only 1 degree Celsius or something like that the temperature increased? Well, that's because only 1% of this energy goes into the atmosphere. A little bit goes into land, a little bit is being used to melt the ice, but most of the energy, more than 90%, is being stored in the ocean. The ocean, and as I explained this last week, has a much higher heat capacity and can store all the energy. And we know this, a swimming pool, for example, takes much longer to heat than a greenhouse. So the situation is that more than 90% of this is being stored in the ocean. And that was the pool house effect that I mentioned last week, not the greenhouse effect. And if the energy would have been stored in the atmosphere, if we were a planet, if we had a planet without an ocean, then the air temperature would already be, the global mean air temperature would already be 55 degrees Celsius, 135 degrees Fahrenheit, everywhere on average, and not the relatively comfortable 18 degrees Celsius, 64 Fahrenheit. So without the ocean, we would basically not be able to live anywhere except at the pole region. And the same for most of the animals. We would all have to crowd at the South Pole and the North Pole. And so you really understand from this that the changes that we notice are much, much smaller than the changes that are actually happening and that we can detect with all the observing systems we have. So when it comes to climate change, the ocean never forgets because it has a much longer memory. And so even if we today would reduce all the carbon emissions that we are doing, even if we stop everything, we would still have a very warm ocean, and the ocean would continue to warm for a long time because the Earth's energy imbalance would still be very high and sea level would rise and all these things would still happen. So we have basically committed to a very large change in the future. So what about other modern global change? Is this just climate change that we are talking about, or are there other things happening with the planet that are connected to climate change? Well, the things that I would like to look at is here really look again back to the Earth as a physiological system, a life support system for many species. It's not just a life support system for humanity. And when we look at this, we understand that everything is about the flows of energy and material between the life support system and the community. And this community may be a group of human beings, it could be a group of elephants or lions or the whales in the ocean. All of them have to take something out of the life support system to sustain themselves, and then they give something back to the life support system, which the life support system needs to absorb. And the limitations, basically the limitations in the flow determine how a community can grow. If there's not enough food, for example, a group of animals cannot grow. They can only have so many offspring that they actually can feed. And that's true for human beings and it's true for all animals. But in the case of human beings, these flows are regulated by ethical, social, and very recently by economic rules. Social rules and ethical rules have always controlled how human beings take something out of the life support system, out of the environment, and how they give it back. But the economic rules have come in the last 250 years and control those flows. And the most important point I want to make here is that the flows have accelerated in the last 200 years enormously. And that's something that should really sink into our understanding. And I want to show you this in the diagram where we looked at the changes in the flows over the last 12,000 or 10,000 years before 1900, before we really started to change the flows rapidly. So for example, air temperature was changing by a very, very small degree per century. Carbon dioxide was almost stable, sea level was stable, the population was growing by 16 million per century. The energy consumption of human beings was very, very little increasing on the order of 0.01 terawatt per century. And the inequality, which we can measure with something that's called the Gini coefficient among human beings, was also very slowly increasing. So then we can look at the last 100 years, and you can see that everything is increasing much, much faster. And if we look at numbers, we can see that energy consumption in the last 100 years increased 1,600 times faster than throughout the Holocene. And with very high energy available, we were able to produce nutrients. We were able to change agriculture from a kind of solar-based, animal-based agriculture to fossil fuel-based agriculture. And with this, we were able to add 5.5 billion people, 350 times faster population growth than through the period before 1900 to the population. So the population growth was only possible because we had energy growth. We had energy to actually change the way we produce food and the way we were living. And then we can see that carbon dioxide, of course, also in the atmosphere increased 600 times faster as a result of our energy use. And air temperature increased 100 times faster, and sea level is still lagging behind because it takes a long time to melt ice and actually warm the ocean. and make the sea level rise much faster, but we have committed to a very large sea level rise already that will happen in the future. And another side effect is that inequality in humanity has increased rapidly as well. So this is really what we did is we had a period, a very long period of stability. And then the 20th and 21st century became change, very rapid change, imbalance, disequilibrium, and that makes the future very uncertain. So I think that summarizes the situation relatively well. Another thing that I want to point out is that humanity has changed in terms of the dominance of the planet. In 1900, if you take all the animals that have a weight of 2 kilograms or more, 4 pounds approximately, then those animals accounted for 90% of the biomass that is animals, and humanity and our livestock was only 10%. Today it's the opposite. We are 90% with our animals, and the rest of the biosphere is only 10%. So we have completely replaced what was living out in the wild by human beings and our livestock. So when you look at these numbers, human environment, 300 million tons of humans, 700 million tons of domestic animals, and we have only 100 million tons of wild animals left. We have 400 million domestic dogs, 200,000 wolves. We have 600 million domestic cats, 40,000 lions, 1.5 billion cows compared to only 900,000 African buffaloes. And our 20 billion chicken you can compare to 50 million penguins. So we have really changed the planet in the last 100 years, very rapidly and extremely. So we are a very dominant species, and modern climate change is not the problem by itself. It's not the cause. It's a symptom in this syndrome of modern global change, not the cause. So what we also see is that modern climate change is increasingly causing cascading changes. So it's actually contributing to make the syndrome much larger. For example, a lot of extinction is happening now because of climate change that has been caused by human activities. And so the changes in wildlife are increasing because of climate change. And what we also see is that we have a large number of weather-related disasters that are increasing rapidly. We see all over the world flooding events that we have never seen before. We see droughts that are lasting much longer. The droughts and high temperatures combined increase the wildfire risk, not just in Australia, which are the two lower pictures, but also, for example, in Siberia. And even last month, we had big wildfires in Siberia or in Russia that were actually going all the way to the ruins of the Chernobyl nuclear reactor and causing radioactivity coming up into the atmosphere. We have stronger hurricanes. We have hurricanes and cyclones in areas where they are very seldom happened before. And so we are seeing a huge amount of changes that are happening because of climate change. And some people are talking about whether we are really in the Anthropocene, that means the epoch of our making, or whether we are approaching a Pyrocene where the burning planet will have a much bigger impact on what is the future of the planet than all the other things. So we really see that climate change is contributing to global change now. And we also see that we are causing a huge amount of massive harm with what climate change is causing a huge amount of massive harm. For example, the migration. When you look at the diagram on the right side, you can see that since 2009 to 2018, the number of people who had to leave their home involuntarily is increasing rapidly. They cannot live anymore where they were living. They cannot produce food anymore where they were living. They have social unrest because of climate change, and they have to migrate. And when you think that we have a normative ethics that tells us we should not participate in creating massive harm, that was, for example, used to judge what the Nazis did in Germany as something that was totally unethical, then we are participating, all of us, today in creating massive harm by allowing the climate to change as it is changing, or by causing the climate to change as it is changing. And another point, the last point I wanted to make here, is that the Holocene was a safe operating space for humanity. And in a very important scientific paper, some of the leading scientists identified 9 global boundaries for this safe operating space. And those global boundaries include, for example, freshwater consumption, land use changes, loss of ecological function and extinction, climate change, novel entities, and ocean acidification, among others. And then they looked at which of those boundaries did we already cross? Are we outside of what the safe operating space for humanity was? And when we look at land use, for example, we see that we have since 1700, where we were using 1% of the Earth's surface, now we are using almost half of the Earth's surface for our use. No space for other animals if we consider this. So land use is one of the things where we are very close to crossing the boundary of a safe operating space. And then, of course, I mentioned that already we have changed the nitrogen and the phosphorus cycle to produce all the nutrients we need to feed the population growth and the growing population. And a lot of those nutrients run off into the ocean and cause a lot of dead zones. The map shows all those dots are dead zones where basically the ocean is dead. Nobody can live in there. Animals, fish that swim in there don't have oxygen and they will die because of the lack of oxygen. So we have created this. And then, of course, we have caused extinction to increase very rapidly. If we look at the long-term rates of extinction, the background rates, then the extinction of birds today is 300 times the background rate. And for mammals, it's 80,000 times. And one of my colleagues, James White, said, we are the asteroid. We are the ones who actually are changing the Earth system very rapidly and causing animals to die very rapidly. Then, of course, we changed the carbon cycle. But it's not just climate change that is a problem. The carbon cycle also leads to much more carbon going into the ocean. And there's a risk that the ocean will be overloaded with carbon. And if that happens, there will basically be no life in the ocean possible. And this frightening publication in 2017 estimated that this might be happening by 2100 plus minus 50 years. So it could already happen by 2050 that we lose life in the ocean. And I think that's, in my opinion, a very frightening perspective. Another thing is that new things are occurring that we didn't know before. For example, in the North Atlantic, on the Atlantic, we see a rapid increase of seaweed, sargassum, that is then polluting or beaching on some of the islands. And then sometimes you have up to 3 meters of sargassum on a beach and nobody can use the beach. Barbados, for example, had several times now national emergencies because nobody could go on the beach, and when it's decaying, it's impacting the people and the health. So we see new phenomena emerging, and we definitely have left the safe operating space. And we are rapidly increasing. And then we are putting more and more new stuff into the environment. An example is plastic. We have an urgent challenge of plastic, which is going to a very large extent into the ocean and overloading the ocean as well. So I'm not going into the details, but that's a very big problem of new and novel entities that we have introduced in the environment. So to finish this point in describing the syndrome or the fire or whatever you may call it, we can say that during the last few hundred years, humanity has made very large and very rapid planetary changes. It has accelerated and introduced new flows in the planetary physiology. And the system is very far outside of the normal range. And it is in the transition into the post-Holocene. So when we look at this, we still haven't really understood, why did humanity actually do this? What was the reason? What is the root cause behind what we are seeing here? Well, and that leads me to the diagnosis. The first thing that I want to do here is to compare the energy humanity is using in 1 year to some of the big geological events. One thing, for example, the big earthquakes that happen a few times in the century, they use energy, they occur sometimes, let's say, every 50 years or so. And they use energy, which I write here as 10 to the power of 19 joules. The Tambora volcano eruption was a very big one, 200 years, a little bit more than 200 years ago in 1815. It caused an ash cloud that went all the way from Indonesia to the east coast of the United States, caused a year without summer in Europe, and it has something a little bit more than 10 to the power of 19. The Toba eruption happened 75,000 years ago. It almost was the end of humanity. Only a small group of human beings survived this volcano eruption and then had to repopulate the planet. And this has 10 to the power of 21 joules. And the big 2-kilometer impactor that comes every million years, or on the order of once in a million years, is at 10 to the power of 22. And now I made this diagram some years ago before I had to give a presentation the next morning. And it really frightened me when I put in what humanity is using in 1 year, because humanity in 1 year is here. So we are basically several Tambora eruptions. We are Toba eruptions in a year, and we are a big 2-kilometer impactor coming to the hitting Earth every 20 years or so. So that means when we see this and how much energy we are using and how we are changing the planet, then it's probably not wrong to say that this is a single species cataclysm. And I came up with the idea that Homo sapiens is a cataclysmic virus in the Earth's life support system. So we have become from a part of the ecosystem in the world, where we were a part like everybody else, running around, trying to get food, grow our population a little bit, have a decent life. We became into the virus. And since I did this, I think I did this in 2015, I've been thinking about, can the virus transform itself into the healer? Can we become actually the healer for the Earth's life support system? Or is it basically our destiny to be the virus and destroy our life support system until we cannot live here anymore? So that's my fundamental question that I want to answer or discuss a little bit next week. Before we do that, let's see a little bit more how we got there. And one thing is, we are out of scale. There is a scaling law that connects all groups of animals. And the scaling law basically says that the metabolic rate, the basic energy that we need to stay alive, is basically depending on our mass to the power of 3/4 times a constant. And that gives us the energy that we need to get into our body every day so that we stay alive. And humanity fits into this. So we like all the other mammals, we fit into this, and we use between 50 and 100 watt, depending a little bit on the weight and the age and the gender. But that's the energy we need. We need to eat this energy every day so that we stay alive. And when I looked at this, I thought, but there's actually an extended metabolic rate, because we use far more energy. We have air conditioning, we have cars, we cook our food, we fly around in the world, we do many, many different things, and we have a total energy consumption that's much, much higher than this basic rate. And it's actually on global average, 2,835 watt. And when you use this equation at the top to compute what mass would an animal have that needs 2,835 watt to stay alive, well, it would be 10 metric tons. So I looked for the animal, which animal has 10 metric tons, and I could only come up with 2 elephants. There's a blue whale, for example, that has this mass or a little bit more, but I had to go to 2 elephants. So humanity has extended metabolic rate that's equivalent to 14 billion elephants on the planet. And 2.7 billion of those elephants are in the United States because the extended consumption is much higher in the United States than in many other countries. So what humanity did is we put a very big load on the planet. And I think that's a very important point to make. But then we need to understand why were we able to break the scaling law. And I realize I'm very close to the end of my time, but maybe you can spend another 5 minutes with me to finish this thought, why humanity was breaking the scaling law. One thing is, of course, we have a very remarkable human brain. And the brain is the most energy demanding part in an organism. The brain to body ratio is limited by the energy that we can make available to our body. And for example, the great apes like gorillas and orangutan, they need so much time to get the energy for their big body into the body that they cannot afford larger brains. They cannot do that. It's from an energy point of view not possible for them because they have a body that is too large. And the human brain represents only 2% of the body mass, but it uses 25% of the metabolic rate. So supporting a large and more efficient brain requires that we somehow get high energy that's easy to process into the body. And human beings did this by starting to cook their food. When we started to be able to utilize fire, we actually were able to develop a much larger brain. And that brings me to this kind of history of humanity, which started a long time ago with increased food and efficiency, which allowed us then to develop a much more efficient brain. And then with agriculture, we were able to reduce the time needed to obtain food, so we could spend time for other things. And then we were able, when a group of human beings started to colonize the rest of the world, we were able to access material and resources that were not available to individual groups before. It was mainly a subspecies from Europe that actually did this. So when you look at it from outside, it was only a small group that went out into the world and started to colonize. And then a very important thing happened, and that was in 1770, around 1770, that Adam Smith redefined the purpose of economy and made it the goal was to reduce extreme poverty and get out of it. And he came up with a new idea about how to do economy. So then humanity started to have easy access to energy, easy access to technology. And with this, humanity was very fast able to develop very rapidly, change the flows and grow extremely into the dominant species. The point I want to make, and that's the last point I want to make today, is that Adam Smith made a very important decision. He basically said, we need to increase human wealth. And that was very, very important for him. And then later economists came in and said, the best way of doing this is to consume more and consume more. So when Adam Smith published the book in 1776, An Inquiry into the Nature and Cause of Wealth of the Nation, he made the assumption that if everybody is more or less independently seeking their best, then this will produce the best result for the community. And he also made the assumption that we don't have to worry about the planet. The planet is infinite. We can only look at human wealth. And in 1776, this was probably a reasonable assumption because humanity was very small. We didn't have any tools or any technologies. We had very little access to energy. And so there was no need to think about the planet because nobody thought at that time that humanity would ever be as powerful as we are today. So increasing the flows became the sole means of economy to create and build human wealth. And that became in the 1930s more and more an idea of the only way of increasing the economy was by consuming more. And Victor Lebov in 1955 basically said, we seek our spiritual satisfaction, our ego satisfaction in consumption. We need to things consumed, burned up, replaced, and discarded at ever accelerating speed. So consumption became the source of growing the gross domestic product, growing our wealth. And so advertisement was brought in place. So make people use more, consume more. And in 1970, Milton Friedman then argued that the sole purpose of a business is not to serve people, is not to make sure that people have what they need. The sole purpose is to generate wealth for the shareholders. And that led to globalization. And with globalization, with consumption, we introduced all these new flows, not going through the details here, but plastic is a very good example how you can grow something and make it, use it, burn it, throw it away, consume it, and make new stuff. So the lifetime of plastic is 100 to 5,000 years, but most of the use times is much, much, much shorter, and the production contributes as much as 40 million cars. And so we have a really big consumption here. At the same time, this new economy introduced an inequality of emissions geographically. You can see that in 1901, most of the carbon dioxide emissions came from the UK, Germany, and the United States. In 2016, it's a little bit more distributed, but when you look at the per capita use, then you can see that the North America, the oil-producing countries, Australia, are the ones that are really at the top in terms of per capita use. And then when you look at in terms of wealth distribution and emissions, you can see with these diagrams that are now on the right side, that the richest people are the ones that are really contributing to the emissions. And even in each country, it is in the way that those who have more are also causing more of the problems that we have today in terms of emissions. So to come to the end, we saw that the baseline was very stable. The planet was very stable, and during the Holocene, it was exceptionally stable, a safe operating space for humanity. Then in the last 100, maybe 200 years, humanity has made very large and very rapid planetary changes in the flows of the planetary physiology. The system today is far outside the normal range and in a dynamic transition, which I would call the post-Holocene. And the diagnosis is that the easy access to seemingly unlimited energy allowed humanity to make those changes in the Earth's physiology, and it allowed us to sustain a rapid population growth. Actually, the growth is more an explosion, and it allowed us to increase the demands, the flows, and build an economic system that was depending on growth and that is depending on changing the flows and increasing those flows, which in my opinion turned human beings into the cataclysmic virus in the Earth's life support system. So, and next week we will then look at what the prognosis is, where are we heading with this, and is there therapy that could help us to actually change this and become the healer in the Earth's life support system. Thank you.
Thank you so much, Professor Plag. It's sobering, but it's important for us to know. And I just wanted to welcome those of you who are coming in for coffee hour. We started a little bit late with Dr. Plag, and so we will begin coffee hour in just a moment. But Dr. Plag, very grateful for your being here. And just one question maybe that you could address next time, and that is, how do we factor something like the novel COVID-19 virus? And that just hold on to that, because your comment about humanity becoming, in a sense, a virus, and the question of how we can turn that into a healer is, I think, for religious people, an ethical question, an important ethical question for us to grapple with. So thank you again for today, and we look forward to hearing you next week.
Okay, thank you.
Thank you, Professor.
Okay.
And I'm going